Welcome to the lecture for solving indeterminate structures using deflections and integration. This first part is going to go through the very beginning of this problem, where we're going to solve for the reactions A, B, and C using just integration over and over, and the boundary conditions that we have gained from these three will help us solve for the extra reaction we have right here. Right, we had too many reactions before when we were working based on the idea that we would be statically determinate, but now that we have deflections giving us an extra equation, we can solve for these extra reactions. This first video is going to go through just the shear and moment functions. It's meant to be viewed around March 27th is the playlist this goes with. Previously, with what we've learned so far, if given a problem like this, where we've got our four reactions and we have no equations of condition, we'd find this impossible to solve. We would not be able to solve for the reactions at A and B and C, because we've got these three reactions in the y direction and a reaction in the x direction, and we don't have any equation of conditions. So we've only got our equilibrium equations at the summation of force in the y direction, and it's got to sum to 0, and that's going to end up being, AY plus BY plus CY, and we can do our moment equation. Let's do the moment about A. That's going to be minus 1 kip per foot, times 12 feet. And the moment, defining this as positive, is going to be By times the lever arm of 6 feet plus Cy times the lever arm of 12 feet minus 12 kips. That's the 12 kips from 1 kip per foot over 12 feet times the lever arm of 6 feet to the centroid of that rectangle. And then, of course, a summation of force in the x direction. I'm not going to take time to write that down. Presumably, you can all go ahead and see that the reaction A in the x direction is going to just be 0. But that's got two equations for the three reactions in the y direction that we want to solve. How can we move on from this? Well, with deflection now being considered, we can now add a boundary condition in the form of saying that the deflection at these 3 points has to be 0. So we can add that the deflection at A or B or C has to be 0, and that's going to give us an additional equation for these things. So that's going to require a lot of work, but it is certainly possible. So we can add arbitrary numbers of reactions and solve for all of those reactions now, as long as we know what EI is. Right? In this case, I'm just saying that the Young's modulus and the second moment are constant throughout the length of the beam, and that just means obviously we can just divide them out whenever we're setting things to 0, because it turns out you multiply 0 by even these very large numbers, it's still going to be 0, huh? So when we're doing this, we've got this. Obviously, we need to find our rotations and our deflections. Rotations we don't have any limits on, right? But we do have limits on our deflection. Our deflection at A, our deflection at B, and our deflection at C all have to be 0. So let's start by looking at our shear and bending moment diagrams. Now, because we don't know what the reactions are, that's the whole point, we're going to have to write these as just functions of ay and by and cy. But that's fine. Right? If we just write this out, let's just draw it again, but as a free body. This distributed load stays the same, and it's still a nice constant 1 kip per foot. And we've got some force, we don't know what it is, at A in the y direction. We've got some force, we don't know what it is. At B in the y direction, we also have some force, don't know what it is. At C in the y direction. So if we start moving from let's call that x1. If we start at AY and move, we progress from A towards B and C, we're going to have the shear as function of x1. Well, that's just going to be AY. That's a constant, don't know what it is, but it's a constant, minus our distributed load, 1 kip per foot, times x1. Alright, that's just the integral of this, which is -1. We can do that in our heads. But there's going to be a discontinuity in our shear function at point B, because at point B we've got this point load right there. So let's just start a new x-axis right there. So this is just the shear from A to B. We've also got the shear from B to C. That's going to be a function of x2. Now that's going to be equal to all of the shear that we put into the beam up to this point, right? So that's going to be equal to, well, AY and BY less this distributed load up to this point. So that's going to be 1 kip per foot times 6 feet. I'm just going to write 6 kips rather than write out 6 feet times 1 kip per foot. And the slope of the shear diagram is going to be the same. All of these are constants. It looks pretty ugly, but it's just a bunch of constants. So minus our 1 kip per foot times x2. And then once it hits C, we don't need to worry about a diagram. It'll just pop back up to 0 based on what C is, unless we mess up the math somewhere along the way. So now that we've got these two functions, and we've got them set up as functions, determining the rotations and the deflections, well, that's just going to be a matter of integrating these functions over and over again, and then picking the right values for their constants of integration to make sure that we obey our boundary conditions at A and at B and at C. So let's go ahead and start with that. Oh, okay, I really should have written what I was going for, which is the moment. We'll do that here. The integral of the shear function from A to B as function of x1 is equal to the moment from A to B, which is going to be a function of x1. Okay, so integral of that of A y minus x1 kip per foot. Real easy. AY x1 minus x1 squared. I'm gonna move this this foot unit down here. But that's all that is, just the integral of that. And then I'm gonna write this more sensibly this time. The moment from B to C is gonna be a function of x2, the one starting over here. That's going to be the integral of this shear function, AY BY minus 6 kips minus x2 times 1 kip per foot. Please don't fall asleep, computer. Damn you. That's going to equal AY plus BY minus 6 kips times x2 minus x2 squared over 2 feet times kip. Run out of space, but there is a constant integration here. I call that C2. Put a constant integration here for C1. Why not? But when we look at these two, we can right away say, okay, well, what's our boundary conditions for the moment? Well, the boundary conditions for the moment from A to B are going to be that, well, the internal moment at A, being that there's no internal there at all, that better be 0. And the internal moment at B is the internal moment at B. It sounds, it's a tautology, but it's true. And that means that when we put in 6 for x1 in this function, we have to get the same thing as when we pop 0 in for x2 in this function. Let's continue on the next page.